Alright, so in this video we'll be going through general concepts of proofs in discrete math. So to begin, I'll give a brief overview of the main types of proofs as shown on the screen, and then I'll subsequently provide an example of a common proof of that particular type later in the video. So let's just begin with probably the least controversial method of proving something, the direct proof. We initially begin by assuming that the logical statement P is true, and our goal is just to make our way to showing that Q is also true through existing axioms and theorems and lemmas, etc. So it's pretty simple. Moving on, the second proof method, and probably the most popular of them all, is proving a logical statement through contradiction. This specific method of indirect proof is pretty neat in my opinion, as we start by assuming that the opposite proposition is true, and this leads us to a contradiction. So say for example we have P implies Q. We assume that Q is false, so we have not Q. Then we make our way from not Q to P, and attempt to find some contradiction on the way. Our third and final proof for this video, or proof method for this video, is to prove the contrapositive of a statement. And this works as the contrapositive of a statement and the statement itself are logically equivalent. This is actually quite similar to a direct proof, where we start with something and make our way to another, but instead we utilize the contrapositive. So instead of starting with P and showing that P implies Q, we begin with not Q and show that not Q implies not P. And by showing this, we have proven that P implies Q. Now, there are many other methods of actually proving, for example, proving by mathematical induction, or proof by exhaustion of cases. But I'll save these for another video since they actually take quite a great deal of explaining to understand, and will take, quite a while. So moving on to our first example for our direct proof. We'll do a very basic proof of showing that 1 over 1000 minus 1 over 1001 is less than 1 over 1 million. So here we have a statement, and our goal is to show that it's true. So we can start with the left-hand side, as we have two separate fractions. So we'd obviously begin by cross-multiplying. So we get 1001 minus 1000 over 1,000,000. We simplify this further, we see that the numerator is 1, so we have 1 over 1,000,000 and 1000. So now we multiply both sides by 1,000,000 and 1,000,000 and 1000, and we see that the right-hand side is in fact greater than the left-hand side, therefore QED. But there's something quite wrong with this proof, with this direct proof. Maybe you guys can pause the video and figure out what the problem with this direct proof is. So relating back to direct proofs, I stated that we begin with something that we know is true, so P, and through that deduce that Q is true, through algebraic manipulation in this specific example. Well, the statement that we started with, the 1 over 1000 minus 1 over 1001, is less than 1 over 1 million, we didn't actually know that this was true. So we aren't actually allowed to start with this as P in our proof. So in other words, this proof is written backwards. And I encourage you, whenever answering a direct proof question, to do this part on a scrap piece of paper or something. And for your legitimate answer, write it backwards so it's logically correct. So you'd start with 1,000,000 is greater than 1 million, and then make your way to show that 1 over 1000 minus 1 over 1001 is less than 1 over 1 million. So that's pretty much the only thing that you have to worry about when proving something directly, is just accidentally writing it backwards. So moving on to our example for a proof by contradiction, we'll make attempt in showing that the square root of 2 is irrational. So in cases like this, I personally can't think of any other method to use besides proof by contradiction. So in this example, we know that the square root of 2 is indeed irrational, but how would we go about proving it? Proof by contradiction. We begin by assuming that Q is false, i.e. in this case, assume that root 2 is rational. So from this, we know that any rational number can be expressed as a ratio of integers. So we know that root 2 can be written as a over b, where we may assume that the greatest common divisor of a and b is 1, as we don't want any common factors, where a and b are integers, of course. From this, we simplify by squaring both sides and multiplying the b squared over. From a very basic axiom, we know that a number is even if it is equal to 2 times some integer. So a squared is even, as it's equal to 2 times b squared, where b squared is just an integer. And the only way that a squared can be even is if a is even. So we know for a fact that a is even. What do we also know about even numbers? They can be written as 2 times an integer. So let's just say a is equal to 2k, where k is some integer. So substituting this back, we have 2b squared is equal to 2k all squared, which is 4k squared. Dividing through by 2, we get b squared is equal to 2k squared. And then from this, we can also see that b squared is even, implying that b is even. But we had previously stated that the greatest common divisor of a and b is 1. But them both being even implies that they share a common factor of 2. So hence a contradiction has arisen. Hence we deduce that the square root of 2 cannot be rational. Alright, moving on to our final example for a proof by contraposition. We're given a statement, prove if n squared is even, then n is even. So taking the contrapositive of this statement, for example, moving from p implies q to not q implies not p, we reconstruct the statement to say prove if n is odd, then n squared is also odd, which is also a much easier statement to prove, hence why we use the contrapositive. So to begin, we assume that we have some odd integer n. As we know from basic arithmetic, any odd number can be written as 2 times an integer plus 1. As we want to move from n to n squared, we want to square both sides, so we get n squared is equal to 2k plus 1 all squared. Expanding the left hand side, we see that n squared is equal to 4k squared plus 4k plus 1. Factoring out the 2 from the 4k squared plus 4k, we see that n squared is equal to 2 bracket 2k squared plus 2k close bracket plus 1. Since n is equal to 2 times some integer plus 1, we'll call this integer m in this case, n squared is also odd. Therefore, we have proved that the contrapositive is true, implying that the original proposition is also true. And that's all for this video. Thanks for watching.